In this video, you will learn about different chemical formulas, functional groups, and how to name simple hydrocarbons. Firstly, let's look at the different chemical formulas. There are basically four types. The first one is a molecular formula. This is a basic formula that tells you the number of atoms you have of each element. So essentially what you do is you write out the symbols of the atoms. Now because we're dealing with organic chemistry, so obviously it will have carbon and hydrogen. Do you know what kind of compound this is? Well, if you don't, then you would in a few minutes. In this case, you have 3 carbon atoms. The subscript indicates the number of atoms you have, and you have 8 hydrogen atoms. Next, we have structural formula. This shows how the atoms are bonded to each other. In this example, you can see that the CH3 is bonded to a CH2, and that is bonded to another CH3. Next, we have a displayed formula. The displayed formula represents the molecules by showing all the atoms and all of the bonds between those atoms. It's actually a very painstaking job to draw this out. So in this case, we have a C3H8 molecule. And so you would draw the 3 carbon atoms in the center, and then you can see you would show the bonding between the carbon and the hydrogen and also in between the carbons. Last, but definitely not the least, is the skeletal formula. This is the chemist's way of writing formulas. Listen, we're lazy people. We do not want to draw out a displayed formula or even a structural formula for that matter. So what we do is we draw a skeletal formula. They basically look like lines, but each one of these lines means something. Every corner is a carbon atom. So you do not draw out carbon and hydrogen, but apart from that, every single element has to be drawn out. In this example, as you can see, the OH is written out. But apart from that, carbon and hydrogen atoms are not drawn out. And as I said, every corner represents a carbon atom. So in this case, how many carbon atoms do we have? Yes, you guessed it correct. That's 2. And each one of them is going to be bonded to hydrogen atoms. Now, if you do not see a double line, it means that it's a single bond because we're drawing out covalent bonds. So if this is a carbon, it's definitely going to be bonded to 3 other hydrogen atoms. In this case, the carbon here is going to be bonded to 2 other hydrogen atoms, but you do not need to draw that out. Next, let's look at the homologous series. So you will hear this term a lot in organic chemistry. A homologous series is basically a series of compounds with the same functional groups. Actually, let me correct myself. The term you would be hearing a lot is functional groups. So it is essential that you know what that means. A functional group is basically the OHs or the double bond or the triple bonds that we have in the compounds. So we will look at the most common functional groups that exist. Firstly, we have an alkane. So what does an alkane look like? Well, just a simple carbon, 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 right? And you have your hydrogens bonded to it. So as you can see, they're all covalent bonds, simple covalent bonds, single covalent bonds as well. Then we have an alkene. An alkene, the speciality of it is it has a double bond. So it's C double bond C. And then accordingly, you would attach your hydrogen atoms. Next, we have alkyne. Well, no points for guessing. If this is a single, this is double, then an alkyne is going to be a triple bond. Yes. And then you would have your remaining hydrogen atoms. Well, I was just trying to highlight here, not basically right over it. I just didn't want it to be misleading. Okay, then we have a halogenoalkane. So halogenoalkane, the name gives it away, is a halogen. So if you go back to periodic table chemistry, halogen is group 7. Yes. So you have a simple alkane, so you have your regular alkane, but with a substitution of an alkane. For example, a chlorine. It could even be a bromine. It could be a fluorine. It could be anything from the group 7. Okay, so that is a halogenoalkane. And then we come to our alcohols. So you have CCC. It's all single bonds as well, but you have an OH. Yeah? So this is CH3. This could be CH2, and that is an OH. So this is actually ethanol. Yeah. Then we have our aldehydes. So an aldehyde basically has a CO bond. This is a special bond. It's a carbonyl, and we're going to talk a lot about it. Okay. So this is a carbonyl, by which I mean this thing, the CO. That is a carbonyl. Okay. And that also forms a lot of other functional groups. So you're going to see that a lot. So let's draw that again. Yes, so that is a carbonyl. When the carbonyl is attached to a hydrogen and another carbon, that is an aldehyde. But when the carbonyl is sandwiched, so you have CH3s, or it could be any amount of carbon atoms, but it needs to be sandwiched between two carbon atoms. Then that is a ketone. So this is an aldehyde, this is a ketone. Do you notice the difference? So here, as we said, an aldehyde is attached to a hydrogen, but here on both sides you have a carbon. Yeah, not necessarily a CH3, you just need to have a carbon on both sides. Okay. Next we have a carboxylic acid. So a carboxylic acid is basically COOH. That is your carboxylic acid functional group. That is how you identify that it's an acid. So basically you have something of a resonance going on between the COOH. Yes, if you do not understand what resonance means, that's completely fine. I'm going to explain every single thing. Okay, so this is a COOH, and then you could have a CH3, you could have a C2H5. As a matter of fact, you could have C7, like 7 carbon atoms attached to it, or 100 carbon atoms attached to it. It could be anything. As long as there's a COOH, that is a carboxylic acid group. While you would also see COO with something else, which is called an ester. And so you could have an ester like this, and you could have something like this. Well, another thing I want to add is, it's not necessary that you will always see carbons drawn out. You could also see something like this. So what does R mean? Well, we're not inventing a new element. R in organic chemistry basically means it indicates carbon chain. So the carbon chain might not be of interest. So basically it is not participating in the reaction. So just to simplify lives, we just write an R, right? Just to make it nicer and crisper and smaller. Next, we have an amine. So this is where it starts to get interesting. So an amine is basically a carbon attached to an NH2. Okay, so this is what you would see in a lot of your biochemistry. If you're taking biology, you will see this in biology. Then we have our nitriles. So a nitrile basically is a carbon attached to a nitrogen. So in this case, this carbon is part of the functional group, okay? And then this guy can be attached to another carbon chain. Notice I'm drawing an R. The R indicates a carbon chain. And then we're moving on pretty much to our aromatic compounds. Aromatic compounds are the ones that contain this guy. Do you remember this? Have you seen this? If you haven't, you're going to see a lot of it. So this is benzene. So every time you see this benzene thingy going on, that is an aromatic compound. And that's pretty much what an arene is. Arene is just benzene, right? And then we also have haloarenes. I mean, you could also have other things attached to it, but this is primarily what an arene is. Haloarenes are basically something like this. And then you have a substitution. Same way, just like you had haloalkanes, here you have chlorine, but that is substituted on a arene ring, exactly, on a benzene ring. And then you have your phenol. So here I have my phenol, right? And then I can have my OH here. And then I can also have acyl chlorides. So acyl chloride is not actually, an aromatic compound. It could be an aromatic compound, but it can also be just, a simple COCl. So the thing with acyl chloride is that it's pretty much an acid which gets substituted. So if you have an acid and that gets substituted with a chlorine, it's an acid that gets substituted with a chlorine. So the OH group gets replaced. That is an acyl chloride. And then we have amides. So an amide it looks like an amine, right? But there's also a CO involved. So CONH2. And then this will be connected to the rest of the ring. Not the ring necessarily. It could be connected to a normal aliphatic compound. An aliphatic compound is your normal straight chain or branch chain alkenes, which are not basically benzene, right? And then you have your amino acids. So for amino acids, you just need to know that it's a compound that has an acid and an amine end, which means one side of it is COOH. So if you're taking biology, you'll probably see it there. And the other side is NH2. So this carbon obviously will also have, two other hydrogens because carbon makes 4 bonds. So this is an amino acids, right? And an amino acid forms amide bonds. So they're going to look like this. When this creates a bond, one amino acid bonds to another amino acid, you're going to have an amide linkage. You would have what is called an amide linkage. Now that we have the rules in place, let's put them in action. So let's look at a simple example. I'll start with, you're going to tell me what this is. So as you notice, there's no double bonds, right? So they're all single bonds. So this is an alkane, yes. So this is an alkane. There are 3 carbons in it. Now in chemistry, in organic chemistry specifically, to denote the number of carbons, we use prefixes. So 1 is meth. No, not the meth that you're thinking about. 2 is eth. 3 is prop. 4 is, can you guess? 4 carbons would be. 4 is bute. 5 is pent. 6 is hex. 7 is hep, right? And actually we can say hept. 8 is oct. 9 is non. And 10 is dec. Okay? For most syllabus, especially for the A level, you only need to know about 6 of them. So this is very important. But it's good practice to know at least till 10. Okay, so coming back to our question. We have CH3, CH2, CH3. So that is carbon 1, 2, and 3, right? It could also be numbered as carbon 1, 2, and 3. Right now, the numbering doesn't matter because we do not have any substitutions on the carbon. So anyhow, because this is 3 carbons, we're going to call it, yes, propane, Okay, so we're going to call it prop. From the prefix, because this is an alkane, it becomes ANE, propane. Next, let's look at another example. What if our propane guy had a substitution? Right, and this is also an H. I did not have to draw a displayed formula, but I just did. Anyhow, so how many carbons do we have? We still have 3 carbons, but how many hydrogens do we have? We now have, if you count them carefully, 7. But we have a special guest here, and that is a chlorine. So we have a chlorine substitution here. Okay, so that changes things, isn't it? So because we have 3 carbons, first of all, we're going to write down prop. Yeah? Now, is this still an alkane? Yes, it's fully saturated, right? There are no double bonds. So when there are no double bonds, we call it saturated. Okay? So propane. And then we have to also take care about the chlorine, right? So where is the chlorine? The chlorine is from either or. Remember, you give the lowest number to the prefix. So that is the first carbon. So because it's on the first carbon, we usually do not write the number. If there's no number written, it is understood that it's on the first carbon. So I'm just going to call it chloropropane. Simple? All right, let's move on. Make it a little bit more fun. Now, what if I had a compound that had 2 substitutions, right? And of course, we're going to increase the number of substitutions, the number of carbons that we have. So I'm going to have a chlorine here and a chlorine here. But the rest of the guys are just my normal hydrogen. So I have a CH3 here, CH3 here. Now remember, carbon forms 4 bonds. So this is 1, 2, 3. So it's going to have another H. And 1, 2, 3. So this is going to have another H, right? So how many chlorines do we have? So let's start numbering our carbons, right? So let's go back and write a number on our carbon. So say this is 1, this is 2, this is 3, this is 4. So what essentially you're going to do is when you see a structure, you're going to start numbering. And what I also did, and did not talk about, was figure out the longest carbon chain. Now, in this case, because we do not have branched carbon chains, it's very simple to figure that out. But sometimes it's not as easy as it seems right now. And I will show you examples for that. So this is 1, 2, 3, 4 carbon atoms. So that is bute. So we're going to write that down. We're going to say that is bute. Okay. And because this is an alkane, because I don't see any double bonds, that is going to be butane, isn't it? Now let's think about the substitutions, yeah? So I'm going to also try to number the carbon chain, the longest carbon chain from the other side. So if I see it from here, 1, 2, 3, 4, yes, hello from the other side. But still, the numbering, if you notice, is the same, isn't it? Do you understand what I'm saying? So either way I number it, I am going to get the same number for my chlorines. It doesn't matter which chlorine gets 2 and which chlorine gets 3 because both of them are chlorine at the end of the day, right? And it also does not matter in terms of other substituents. Even if one of them was chlorine and one of them was bromine, it doesn't matter who gets the lower number, right? As long as you are giving the lowest possible numbers to the substituents. Yes? Okay. So we're going to name this now. Now, when you have numbers, you separate them with a comma. So that's 2. 1 second. My pen. Comma 3. And then every number and letter is separated by a hyphen. So that's 2,3-chlorobutane. But do you feel like there's something missing on here when I call it 2,3-chlorobutane? Is there anything missing? Well, yes, because I just called it chloro, isn't it? Isn't there two chlorines? I should be respecting both the chlorines, right? So I've given the position of both the chlorines, but I'm saying it's only chloro. So that's not correct. It is dichloro. Di in chemistry means two. So dichlorobutane. Now that is correct. And we can now move on. If I have something like this, yeah, and this has, say, this is my normal carbon atoms, CH3. Now I have 1, 2, 3, 4. So this is 4 carbons. So that is, yes, you guessed it correct. That's bute. Now, because this is an alkene, this is butene. But now I want you to think about it. If I just write butene, right? What about if the structure was like this? Are both of them the same thing? Do you see the difference in position for the double bond? Yeah, so there's no way that I can distinguish which one I want, right? And in chemistry, the position of the double bond is very important. Sometimes you can have, a drug, which might be a drug in one specific orientation and might be poison in the other orientation. So all of this is very important. So I should be able to tell the chemist specifically what I'm looking for, right? Or the chemist should be able to communicate that very clearly. So to solve this problem, what IUPAC did was you also have to number the double bond, right? You should be able to tell the position of the double bond. So we can do this in two ways. So either we call this, so because this is on which carbon, so because this is the one that we're numbering, this is 1, 2, 3, 4, 1, 2, 3, 4, right? So we're going to give it the smallest number, so that's going to be number 2, yeah? And because this is on both the carbons, right? The double bond is between the two carbons, you give it the lowest number. Makes sense? All right, so this is going to be 2 butene. Notice there's a hyphen when you have a number. Or this could also be written as butene. Now, this may look odd, the butene may look odd, but it actually becomes useful. It becomes useful sometimes when you have like really long structures, right? And to put the 2 at the start sometimes can be confusing. So then we tend to use it. Otherwise, we just tend to ignore it and, go with the normal 2-butene, which is just simple and sweet. All right, so that's it for this video. See you in the next one.